knowing about the second derivative can help us determine when we're at a critical point whether it's a max or a min. For example, suppose we have this critical point and we know that the derivative at that critical point is 0 and that the second derivative at that point is a negative number. Then we'd know that at that particular point C, because the derivative is 0, we know the function was flat. We also know at that particular point, we also know that it's concave down. The only way it could be flat here and concave down at the same time would be if it looked like this, you were at the top of a bowl. So you would know that you have a relative max in that case. Or if the second derivative, if the first derivative is 0, so you've got a critical point, right, at C, and the second derivative turns out to be positive, you know that it's level at C because the first derivative is 0, and you also know that the slopes are increasing, and so you know that you must be at the bottom of a bowl, so you have a relative min. Okay, so if we have a second derivative, then this might be a nice test because we just have to test the second derivative at our given critical point. If you remember before, when we had the first derivative test, we'd find places where it was level or had a corner, and then we'd look if it was increasing at first. So if the derivative was increasing and then the derivative was either 0 or undefined, and then the first derivative was less than 0, then we'd know that we were at a relative max, right? Whereas if the first derivative was less than 0, so initially the function is going down, and then you have at a point the derivative is 0 or it's undefined, and you have either a corner point or a level spot, and then if after that the first derivative is positive, you'd know that you were at a relative min. So the beauty of using the second derivative is that with the first derivative test I had to look at the derivative on either side of the critical point. So not only did I have to figure out where the derivative was 0, I had to evaluate the derivative on either side to figure out what was happening. The second derivative test is nice. I only have to look at the second derivative test at the critical point I just found. That can be handy, but remember, some critical points occur when the first derivative is undefined. If the first derivative is undefined, it's impossible to find a second derivative. So second derivative test doesn't always work. If it fails, then you can go. Then you'd have to go to the first derivative test to look. Now notice that if f double prime is 0, it's not clear what the concavity is. You could have a function that's kind of super flat here and have the concavity away from that point, right, or have the slope away from that point. It could be a saddle like that, or you could have a function where the second derivative was 0 because the function was really flat at the critical point, not completely flat, but fairly flat, and that would be making the second derivative be 0, and you couldn't tell in this case if the second derivative is 0. This idea of using the second derivative is called the second derivative test. It says, suppose that the second derivative is continuous on some open interval that contains your critical point C. So if the first derivative is 0 and it's concave down, then you must be at a max, right? On the other hand, if the first derivative is 0 and it's concave up, you must be at a min. But if the first derivative is 0 and you don't know about the second derivative, or you know the second derivative is 0, you can't tell whether it's concave up or concave down because there is no the second derivative is 0, then the test fails. You can't really say anything. Okay, let's look at an example of that. So we have this function g. Let's find the derivative. We get 4x cubed minus 12x squared plus 8x, and I see immediately I can pull out a 4x, and that leaves behind x squared minus 3x plus 2. So 4x and x minus 2 and x minus 1 will do it. So we can see we have 3 critical points here, one at 0, one at 2, and one at 1. We can also look at the second derivative. And to take the second derivative, the 3 comes down and we get 12x squared and minus 24x and plus 8. Okay, so what we can do is we can look at each of these points, if we look at this, the second derivative at, say, 0, we get 8. That means at 0, the derivative is 0 when you plug in 0, right? And it's concave up, so 0 must be a relative min. Also, if we look at the second derivative at 2, we plug that in here. Let's see, 12 times 2 squared. 2 squared is 4. 4 times 12 is 48. 2 times 24 would also be 48, so we have 48 minus 48. That's 0 plus 8. So the second derivative is 8 there as well. So we know that at 2, the graph is concave up, the level right there. So we have a relative min at 2 as well. And let's look at the second derivative at this last critical point at 1. If you plug in 1, you get 12 minus 24, that's negative 12, plus 8. Negative 12 plus 8 is negative 4. The second derivative is negative there, so we have the function is concave down at 1. So we know there's a relative max at x equals 1. So the second derivative can quickly tell you whether you're at a max or a min.